Hi everyone. This is our group. My name is Ming Geng,
I'm Nathan Mower.
I'm Ricardo Paez.
and in our group, we're doing a bicycle computer. Just like our title, we have come up with a one-chip solution to improve hardware quality, speed accuracy, and sensor latency of a commercial bike computer. So what a bike computer does is that it calculates and displays trip information, similar to the instruments in the dashboard of a car. So this is our functional block diagram. For an overview, first we have data from a Hall effect sensor installed on a bike that will be read in as a bit stream. The data will be converted into various computations, saved into memory for future access. And finally, the data will be displayed on a screen to the user. The focus of this project will be on achieving an effective bike computer. So these are our modules. We have a Hall effect sensor, distance travel computation modules, speed computation modules, memory modules, and display module.
So to explain the Hall effect sensor, one of the distinguishing features of this is that one, it's mounted onto the frame of the bicycle, and the sensor reads a magnetic field, and what generates a digital output on and off is the use of a Smith's trigger, which gives us that bit stream as an input. And in the speed calculation, we use that same input from the Hall effect sensor, and we generate the speed. We keep track of it with the counter. Whenever the speed does not change, it will display the last stored speed. Otherwise, it'll generate that speed.
So next, talk about the distance travel computation. So like the speed calculation, this also uses the Hall effect data as input. And so it'll read in that Hall effect sensor whenever there's a high, then a rotation counter built within the calculation block increments. And that keeps track of how many times the wheel is rotated. And the distance will increment, of course, with every third rotation of that rotation counter. And the way that that lines up is we have a 26-inch diameter wheel as kind of the default, and we store that distance in a 15-bit fixed point number. So, 1 bit tick up every third rotation for this 26-inch wheel is about, 1/256th of a mile. And of course, in that fixed point value, which is the 15 bits, the first 7 are, reserved for our whole number. Last 8 are reserved for the decimal number. And because of this, our maximum value that it'll store is set to 99.9 miles. Of course, there can be adjustments made to that pretty easily by adding bits at the front. Could go as high as 999 if need be. Of course, fixed point numbers definitely aren't the best solution, but they were chosen for simplicity. But moving to fixed point numbers in the future would really improve our accuracy and, is necessary to support more wheel size options. Okay, next up, the memory. So, of course, the distance traveled, the output of that gets pushed into our memory. The original idea was to have 2 different trips, much like the odometer of a car, where the first trip is sort of independent of the second trip, and they can be counting up at different rates, counting up at different times, basically, and also just be shown at different times. In the end, what was shown in this project, we only have 1 trip that's stored, and that trip will be, it's only updated every 1/10 of a mile. So, for example, if we're sitting at 10.1 miles on the display, it won't be updated in memory or pulled to the display even until 10.2 miles is reached. And, of course, that's a big design choice because our display, we don't want updating every time that increments every third rotation. Otherwise, it would just be updating with pointless information and rewriting over and over again. And because of that, we just didn't want that continual update. Yeah.
So for our display, we're using a blue 16:2 character LCD with an LED backlight. This display is pretty common. They are used by Arduino users. Also, for the display, we implemented an universal controller that is adaptable for most low-power hobby displays to kind of just make this chip more universal and more user-friendly. Also, we're implementing a finite state machine to clear display and to write to display and to enter a new line, depending on the data.
Yeah, and to talk a bit more generally about our architectural choices versus what's available on state-of-the-art chips. Well, first off, state-of-the-art is a little weird here because there's not like research going into this exactly. It's more like commercial products that are available. But, you know, comparing our design to the commercial designs, no less. So first off, the way that we get our data is through the Hall effect sensor, through tracking the rotations of the wheel and so on. Whereas in most commercially available solutions, they're using Bluetooth to connect to a cell phone and either get a GPS signal from the cell phone, or they have a direct link to a GPS. And that way they can track, you know, distance and speed directly through a GPS. Next up, accuracy. Of course, we're using the fixed point 15-bit digits, which limits our accuracy quite a lot, where we would imagine the commercially available solutions are using some sort of floating point number just to increase the amount of accuracy that they have. And then here's where we kind of get into the unknowns. Memory, our memory is very simple. Of course, there's, you know, plenty of ideas on how we can make that and improve that in the future. Most state-of-the-art designs that we've seen are using kind of the dual trip odometer style, or style that's found in cars. So there is some sort of memory usage, memory controller going on there that we would like to achieve. And then, of course, future improvements. If we could get configuration options for our wheel sizes, I think that's one of the biggest differences we have over what's kind of commercially available, because, you know, these bike computers that you can buy from, you know, I don't know, REI or some of these other stores, they're just ready to go right out the box. You just put them on your bike and ride. Whereas, you know, ours, you could do that if you had a 26-inch diameter wheel. It wouldn't work otherwise.
So here we wanted to show our final screenshot of a project before. This is before DRC and LVS, following metal and polyfill. We also have 15 pads, 13 input and output pads, and 1 power and ground. And to show the performance of our chip, we have the power, the clock frequency in the area. We have 0.155 milliwatts. It runs at 125 megahertz, and our total area was 0.546 millimeters squared.
And this is our presentation. Thank you guys so much.